Hi everyone, welcome to the afternoon sessions. It's my pleasure to introduce JayStock. Jay is one of those people, as an anthropologist, who makes me envious, wish I were an archaeologist. Much better time resolution on exactly the kind of questions that interest all of us here. He's a skeletal biologist, but has an intense interest in behavior and uses the modification of human biology and archaeological records to investigate behavioral questions. Also studies contemporary people as well. Please join me in welcoming Jay.
Thank you very much for that kind introduction. I would like to confess right now that I have data envy of most people, well, every talk that I've seen here, compared to what the sort of data and that we can get from the skeletal record, which is really the primary material that I work with. But you'll see that even though I'm a bioarchaeologist and I study human skeletal remains, I've called my research group the Phenotypic Adaptability, Variation, and Evolution Research Group. And there's nothing about skeletons and nothing about archaeology there. And it's because I see the skeletal record as the remaining component of the human biology of people in the past. And what we're trying to do in the group is bridge the relationship between living human biology and past human biology. I think you will notice that this is difficult to do and that we do it very crudely. But that's really the aim of the group. So we study living humans. I'll only talk a little bit about the living human data because the questions that we're asking are really driven by the past. But today I want to talk very broadly about how we start to rethink and interpret very broad biological changes over the last 10,000 years in a few different parts of the world. But I wanted to start just by talking about modern human origins. We know that humans evolved in Africa 200,000 years ago and dispersed out of Africa sometime around 60 or 70,000 years ago, and that this dispersal was a dispersal of highly mobile hunter-gatherers with modern human behavior, with language, art, symbolism, a full behavioral package that archaeologists see as modern human behavior. And this suggests that the colonization of the world was really dependent on culture and technology as an adaptive system. And I want to start from that point, thinking about foragers and cultural change and how cultural change influences adaptability within our species. Of course, once humans dispersed to all parts of the world, agriculture developed independently in many different places. This just illustrates in green the main centers of agricultural origins where different plants were first domesticated. There are more regions than this, but these are the key areas. And the blue are areas that are the most productive today. So it highlights the relationship between cultural change and the fact that environments change as well. So some of the areas you'll see, particularly in Central, East, and West Africa, were centers of agricultural origin but are not centers of productivity today because of climate change. So I wanted to point that out very broadly as context to probably the first major cultural transition that I want to talk about today. And agriculture, there are many implications of agriculture. Of course, increased environmental productivity. You can feed 50 to 100 times more people in an agricultural per area of land with agriculture than with hunting and gathering. And this increases fertility. It leads to birth stacking. So it enhances the cooperative breeding of humans. It leads to massive demographic expansion. But agriculture also can buffer environmental variation because of the production of food surpluses. The food surpluses can lead to task specialization, so people begin to diversify skills into crafts, and that can lead to runaway technological evolution. But I wanted to mention something about the relationship between diet and agriculture as well. We tend to think of it as something that leads to all of these demographic and technological changes, but it also leads to a dramatic decrease in dietary breadth, and that's both it has the advantage of food security most of the time, but it also leaves vulnerability to periodic droughts and food shortages when you're dependent on one or a small number of staple crops, and that especially with a high population. So it can lead to poor quality and risk as well as stability. But some other consequences of agriculture are property ownership, competition, war, disease, the fact that you're sedentary, so living in conditions of poor sanitation, and there's a much greater potential for zoonotic diseases because of the transmission of disease between animals and humans that are living in close proximity. So Jared Diamond, of course, has called this the worst mistake in the history of the human race. Apparently, if you touch Jared Diamond, he spits out articles. I don't know whether I haven't tried that, but I just lifted the first image I could find off of Google Images. And but anyways, I don't really want to talk about the mistake issue. I want to, obviously, there is a lot more than the negative side of agriculture. It's a complicated change in human ecology, and I want to talk about teasing apart some of that complicated change. At a very, very coarse perspective, some of the big transitions, bioarchaeologists tend to focus on the origins of agriculture. Quite a few of them have. But from the origin of modern humans and dispersals out of Africa, the independent origins of agriculture is a big cultural shift that leads to probably the first major demographic inflection point in the history of human demography. Population increase and a rate of increase that's greater than what happened previously. Subsequently, we have, in most parts of the world, there's a very rough chronology of cultural change through bronze and other metal technologies, through the Iron Age and larger villages, medieval period, and the Industrial Revolution. The Industrial Revolution is often seen as the second biggest shift in human productivity, and what the origins of agriculture and the Industrial Revolution share is the emphasis on productivity, on a massive scale of increase of productivity of society, which results in a bigger demographic shift than any of these other transitions. So those two are often seen as underpinning some of the key shifts in human biology and human health that I want to look at and unpack a little bit today. And as a relationship then between culture and technology and our biology, we tend to think of course, natural selection as environments acting on phenotypic variation, which can be a result of either physiology and development or genetic adaptation, but ultimately leading to variation in the underlying genetic diversity of populations. But of course, culture and technology play a dual role in the system, one as a buffer to a buffer of environmental stress, so something that buffers our biology from the need to commit to costly adaptation. If we can adapt culturally relatively rapidly, then physiology and genetic adaptation are largely irrelevant. So it's, in some ways, it's seen as the primary adaptive system of our species, but also perhaps the primary stressor of our biology and physiology and development. So in a broad integrated way, we need to consider the relationship between these two through space and time. So coming to then the raw material that I work with, you can see the sort of humans that I excavate and study are much less. You can see that there's a challenge to extracting the sort of data that many of you have out of my raw material. So as I said before, I'm talking to you with considerable anxiety about how one might view the type of data we deal with. But ultimately, the skeleton is something that records the life history of an individual, and groups of skeletons record something about the history of the life history of those populations. And so the key task of a skeletal biologist then is to try to extract as much information as possible. So in a way, the skeleton's like a book we don't know the language to. We have to try and learn parts of that code and extract as much information as we can. If we open up that book and take a look at the types of information that we can extract, what we typically think of is the kind of CSI model. And my hotel room for the last few days seemed to only have CSI on in the evening, so I got a bit saturated with this. But looking at skeletons and getting the age and sex and learning something about the person. But populations themselves can tell us something about demography in the past. We can learn about health and disease, nutrition, habitual behavior, and adaptation and evolution. And some of these in the red are the types of population level questions and issues that I think we really need to study, and we can use the archaeological record to study. So I'd like to talk about some of the ways we can extract information, particularly about growth and about habitual behavior from the skeleton and how it relates to cultural transitions. The probably landmark volume in this particular field, there are two landmark volumes, both involving Mark Nathan Cohen. One is Health and the Rise of Civilization. He basically pointed out on the basis of a lot of the archaeological record, much of what we know about the transition to agriculture, larger social groups, the fact that there's much greater transmission of disease, an increase in paleopathology, and that primarily the transition to agriculture is a relatively bad thing on the basis of what we can see from the pathology of the archaeological record. But that's a view of the skeletons that looks for disease. And what I would like to do is try and look at human biology in other ways, look at continuous variation in the skeleton and what that tells us about life history and growth and variation. The types of evidence that Mark Cohen points to is also in the Paleopathology of the Origins of Agriculture book in '84, is the vast increase. Almost everywhere where there is a skeletal record of a transition to agriculture, you see an increase in the frequency of evidence for metabolic and nutritional disorders. Some of these lower pictures here are parodic hyperostosis and cribrorbitalia, which reflect likely differences in anemia, and you see big increases in Mesoamerica, for example, in those sorts of diseases, and also massive increases in infectious disease following the origins of agriculture. So things like tuberculosis, Pott's disease, which is related to TB, other diseases like syphilis and yaws, leprosy, all of these you find the first occurrences in sort of urban and peri-urban settings following the origins of agriculture. And so looking at that broad demographic history that I talked about right at the beginning, I wanted to come back to that first of all and say the agriculture and the Industrial Revolution are major changes in productivity, and that productivity is translated into reproduction in one way or another. These could be seen as laying the preconditions for the two major epidemiological issues that we consider around the epidemiological transition. So the origins of agriculture set in motion the disease profile that we see as characterizing our species until very recently, and the Industrial Revolution set in motion the type of cultural change that ultimately led to the decreased incidence of infectious disease and increased immune disorders that we see recently. I'm not saying that, of course, obesity started with the Industrial Revolution in the 1700s, but that the preconditions for the runaway technological development were set in motion that led to these different shifts. And in many ways, this ignores a lot of the subsequent cultural change. It doesn't look at variation through time, but we're thinking very broadly about two major different demographic events, changes in productivity and changes in disease and epidemiological profiles in our species. So I want to talk a little bit about that issue of, this obviously raises the issue of discordance, the issue of cultural change being more rapid than biological change and how populations respond. It raises issues about the timing of change, about what cultural changes are involved and what are the long-term impacts of that change. So those are really some of the issues that I want to try and unpack a little bit. I want to start now by talking about ways in which we can look at longer-term change. Until very recently, people had looked at around the origins of agriculture quite extensively, but not looked at what had happened subsequently or across the Holocene, assuming that it was really only the major transition that's interesting. And so I want to talk about a study conducted by a master's student of mine. It's published it about 10 years ago now, but looking at the relationship between cultural change and stress in ancient Egypt. And if you can see, I don't know whether this will show up on, can you see that arrow on the screen there? Looking at the dentition, when teeth grow, of course, the crown enamel is laid down from the occlusal surface towards the root tip in incremental bands. And as teeth develop, if a child experiences a period of stress, as we all know, linear growth in the body will stop for a period of time until that stress is passed, and then growth will resume once the individual has survived the stress. But teeth don't form that way. Teeth, if you have a prolonged period of stress, they produce poor quality enamel for a little while, and once the stress is passed, then the enamel quality picks up again, and that can leave horizontal bands on the teeth that you can see here called linear enamel hypoplasias. And so we wanted to look at frequencies of linear enamel hypoplasia as a proxy for stress following the transition to agriculture. And we wanted to look at longer term trends than you might find just around that transition. So what we did was look at Upper Paleolithic hunter-gatherers in the Nile Valley, some Badarian or pre-dynastic populations, which are, these are Neolithic. They're just on the cusp of agriculture. They're living in sedentary villages, but they're still hunting a little bit, but they're just starting to farm. And then subsequent populations, a slightly later pre-dynastic population, and two dynastic populations from the 1st and 12th dynasty of ancient Egypt. And looking at the frequencies of LEH, we can see that they triple between the Upper Paleolithic hunter-gatherers and the Neolithic, but that there's a gradual recovery through time by the 12th dynasty. That just tells us that cultural change, trade networks, allocation of resources become more stable and alleviate stress over time. That's something that it's not surprising given what we know about the role of cultural change in sort of ameliorating stress. But it also shows that this transition to agriculture is not as complex as many people have pointed out. If we think, though, about what I'd like to do is start thinking about phenotype, about linear growth and about adiposity, about metabolic disorders. How can we start to track the long-term history of these? Of course, on one level, we know that this is a very recent phenomenon, that I think Jonathan showed this slide. It's a paper published last week in The Lancet showing how post-1990 even there's very dramatic increases globally in obesity. So in some ways we know that this is a consequence of the modern society and modern environment. But I'd like to think about the long-term history of phenotype, because there's good reason to think that these transitions with agriculture and subsequent cultural transitions would influence human biology in similar ways, and that there should be a longer-term history to changes in the human energetic biology. Of course, we're limited in any context by the medical record into looking at soft tissue. So we need to think about ways we can kind of creatively look at phenotype in human biology on a deeper time scale. And of course, the simplest, I mentioned before data envy. Many people have been talking about much more complex models of understanding obesity and diabetes over the last few days. The simplest model is, of course, an energy balance model. And that's about, with the type of data that I have to deal with, that's a reasonable starting point, is thinking about both diet and physical activity as the two key components. Of course, energy balance involves the simple relationship between energy intake and energy expenditure, and the key variable of intake is diet. The key variable of expenditure beyond basal metabolism is physical activity. And those are two things that we can start to think about in prehistory. So that's really what I would like to talk about. How can we track energy intake and activity in the past? This is Jonathan Wells at the very beginning of this conference presented a model that just involved lean mass and adiposity and the relationship between the two, how they're not necessarily correlated to one another and how they change across generations. We know that in this context, fat is something that buffers stress. We also know that it's something that should change with the energetic and dietary changes and activity changes across prehistory. So agriculture, as I mentioned before, leads us to a bit of a paradox of resource security, but also vulnerability. And that leads us to questions about what are the implications on phenotype, and can we track longer-term trends in body size and metabolism. I want to talk a little bit about methodology, because how we would actually get at some of these issues in the past. Stature and size, of course, is something that correlates with lean mass, and that's something that we can measure quite simply through bone lengths. Body mass is a little bit more complicated and may link to adiposity. But very broadly speaking, if we can start to look at mass-stature relationships and how they relate to activity, we can start to track long-term trends in energetic ecology. So very briefly, to talk about the types of methods, long bone lengths are obviously a very simple measure of stature. They correlate very strongly with stature and reflect somatic growth. Body mass is more tricky to measure from the skeleton, and the best methods tend to measure joint dimensions. And the reason that joint dimensions correlate with body mass is that they grow in proportion to mass until puberty. And this is good because it gives us a snapshot of body mass at a particular time of life, but it doesn't represent late life apposition of fat. So it's difficult to track changes that would occur within the adult lifespan, but you can track differences that occur during development quite reasonably. And testing of these methods show that you can estimate individuals of normal weight and over. These are tests using CT scans of living humans. They show that you can estimate the mass of people within a normal weight and overweight range with quite a deal of accuracy using any method, but the methods tend to overestimate the weight of people who are underweight, and they tend to underestimate those that are obese and severely obese. But they do give us a way to start to differentiate those in normal weight and overweight, and particularly normal weight and overweight at puberty. So it gives some indication. We can start to pull apart a little bit about mass differentiation in the past. I think we need to work to try and find ways of accurately identifying mass in other categories, but that's going to be a bit of a challenge since much of that occurs after skeletal maturity. I mentioned activity, though, and that's the key area where my research has contributed, is looking at how we track activity in the past. And the primary means of doing this is through bone biomechanics and cross-sectional geometry. So if you take a femur and cut it in half, you get a cross-section that looks something like this. You can apply engineering principles to the bone as though it were a hollow beam, and then estimate the torsional strength, bending strength, and compressive strength of a bone. These are good because they tell us something about the mechanical performance of a bone, but more specifically, they track activity within the lifespan. And the reason they do that is through the constant remodeling of bone tissue. Our bone changes and turns over about every 7 years. So I've lived in the UK for 14 years, so my skeleton is turned over twice since I've lived here. I'm more British on the inside than I sound. What's also really interesting about this is that if you dramatically change your behavior and increase your activity levels, it exerts strain on the skeleton and leads to adaptive bone deposition. So your bones will get thicker and change in shape and dimension. And if you stop using your skeleton, the bone starts to atrophy. And this disuse category, which reduces the strength and size of bone, is the primary limitation to space travel. It's one of the reasons why astronauts have to run on treadmills when they're in space. It's not because they need to exercise, it's because they need to maintain their bone mass. They need weight-bearing loading to do it. So we know that bone remodels and it reflects activity during life. This is a cross-section of my own arms and legs. You can see here using a PQCT scanner. What we're trying to do here is we can measure the strength of my tibia and fibula here, the strength of my humerus, but you can also see that it gives us a chance, and this is work that's ongoing right now, to measure muscle, which you can see in lighter gray, and the darker gray here is fat. And if you look at my upper arms there, you can see it puts one in a vulnerable position to give a talk and let the audience look inside your body. But looking inside my arm here, you can see quite a bit of this lower density tissue. I like to think of it as low density muscle rather than fat. Actually, if that's a takeaway message, you can think of how I have such a diverse range of muscle in my my upper limbs that it's impressive. But just broadly speaking, I'm going to talk a little bit about work which shows the link between living human bone variation and skeletal variation in the past. And the take-home message is that there is some potential, at least, to start to integrate more with other soft tissue. So not that we can reconstruct or interpret soft tissue variation in the past, but if we can find suitable correlates within the body, we may be able to dig a little bit deeper into past human biology. But looking at variation within humans, this is a study we did a few years ago looking at Cambridge varsity athletes, varsity runners, varsity hockey players, and varsity sedentary controls. You can see a dramatic decrease in bone thickness across the range of, and this tracks very nicely and is statistically significant between groups, with long distance runners having the strongest bones. But you can see there's also a shape difference between runners and hockey players. The AP, the front to back strength here, is a result of constant and repetitive loading in the same direction. The hockey players are constantly changing. They're very active, but constantly changing direction, and this engenders strains in a lot of different directions and leads to a more circular diaphysis. And this was testing some long-held assumptions in the fossil literature about early modern behavior. And so we took the data from varsity athletes and some prehistoric hunter-gatherers and used it to look at early modern humans. Again, and I just want to show a few examples to show that this pulls apart variation and in mobility within hunter-gatherers. What you can see here is this yellow group and green group are small-bodied foragers. These are later Stone Age or Khoisan foragers. These are Andaman Islanders, who are they're hunter-gatherers but are relatively sedentary, depend on marine resources. You can see differences in tibial or lower limb strength between the two. If you put regression lines through those, you see our larger body-sized long-distance runners and swimmers coming apart the same way. So they're differentiated by biomechanical profiles based on their activity levels. And when you look at the earliest modern humans outside of Africa from School and Kafsa, they date to about 90 to 120,000 years ago. They're like extreme versions of distance runners. They have highly strengthened lower limb bones that reflect extremely high activity levels. So then the question is, how does activity change through time, and how can this be used to track variation in phenotype and energetic biology? Some of the archaeology work that I do is based on looking at the earliest sedentary villages. So a few years ago, I ran a project with Lisa Mahar and Tobias Richter in the eastern desert of Jordan, excavating what is, to me, I think it's the first real sedentary village in the world. It's the only, I think it's the earliest archaeological site that's visible from Google Earth. It's a 20,000 square meter mound that is chock full of lithics, as you can see. And the lithics are 3 meters thick, so to produce that many stone tools, you have to live there for a long time with a serious number of people. And this is 20,000 years old, and excavating it contains some of the first hut structures. So you can see, as soon as you dig under the surface, there's evidence of semi-permanent dwellings, which are some of the first architecture in the world. This shows that by 20,000 years ago, long before the origins of agriculture, you have people starting to live in aggregated villages. That's interesting because it suggests that it starts to decouple the mobility from agriculture a little bit. It's not about one major cultural transition. There are a number of other cultural changes associated with this particular period. But subsequently, at around 15,000 years ago, the Natufian period in the Near East is what many people see as crucial for the origins of agriculture. This is people like Ofer Bar Yosef at Harvard have argued that this is really the key time period for the first origins of agriculture in the world, because it's socially complex hunter-gatherers living in semi-sedentary camps with quite considerable exploitation of grain, although it's not domesticated. So you can see things like these groundstone bowls at a lot of sites. So there's evidence for a very diverse range of plant exploitation and sedentism, and some of the first formal cemeteries. But many of these features extend earlier into this period, about 20,000 years ago. So there's a long, drawn-out period before people start actually farming when you see cultural change and complex hunting and gathering. So what I'd like to do now is look both this Natufian period that I mentioned just sits before the first farming villages in the Near East. And that's really the crucial time period with which people tried to understand the impact of farming on human populations in the past. I'd like to try and extend that a little bit now by looking at phenotype both before and after that transition. So starting with the Middle Paleolithic, those really early modern humans that I talked about before, the early Epipaleolithic, so the people who were living in those first aggregation sites I talked about, and then following the Neolithic, what happens as a long-term impact of that transition to farming as you get into bronze technologies and otherwise. Looking at femoral head diameter, or femur length as a proxy for stature, and femoral head diameter as a proxy for body mass, you can see a dramatic decrease from the Paleolithic to the early Epipaleolithic, and a slight increase again in the Natufian, followed by a decrease, and an increase again in the Bronze Age. So a complicated change of fluctuating body size through time. It's not a unilineal progression. Many people have focused on transitions like the Natufian to Neolithic before and said, well, this is the impact of agriculture. But again, it shows the complexity of cultural change and phenotype through time. It's a little bit more variable and difficult to make much out of for body mass. But moving to the cross-sectional properties of bones as a proxy for proxy for activity, I think this is where we can start to get the other side of the picture. There's fluctuating body mass through time, fluctuating stature. We can see a continuous decrease largely in bone strength. This is femur strength, or the upper leg bone, through time towards the Chalcolithic, and then an increase again in the Bronze Age. This increase, I have not plotted this particular plot by sex because some of the early Epipaleolithic and middle it's just not sufficient to do that. We're only talking about a handful of fossils. But by the Bronze Age, you see this diversification, and that's actually a sexual diversification where an increase in sexual dimorphism with time. So there's evidence of both change, but also differences in men and women, and I'll highlight some of those in a few other slides in a moment. But I think the most important thing to take from this is that you see variable body mass, but quite a considerable decrease in activity levels. And that sets some of the preconditions for what we would think of as relevant to metabolic disease. And they seem to track differently through time. And so I've talked a little bit about these trends in the Levant, and what I'd like to do for the rest of this talk is talk briefly about the Nile Valley, Central Europe, and Northern China, where we have similar data to start to track these changes. I mentioned before the linear enamel hypoplasia in populations along the Nile, and I want to explore that very, very briefly again. How did body size, body mass, or stature, body mass, and activity levels change through time? I just threw in a picture, another ad for the British Museum. This is a sculpture from Kerma that's on display in the British Museum, which you can go and see if you have some spare time this afternoon. If we look at stature through time in the Nile, this is very coarse resolution in a sense, but we have from those early hunter-gatherers to the Neolithic, a dramatic drop, and then an increase in stature. But you can see a progressive and consistent decrease in mobility through time. I think that's really interesting as well, because that, body size dropping and then going back up, while activity continues to drop off. Those are, again, preconditions for what we would think of as being leading towards metabolic disease. I mentioned before Central Europe. The Central European Neolithic is really important because it's one of the places where we have really, really strong evidence for the Neolithic driving human evolution. Of course, coming through the evidence of lactase persistence associated with the linear band ceramic. Much of this is Mark Thomas's work, but this is taken from a chapter he wrote with Joachim Berger, showing that the evolution of the Northern European lactase persistence occurred in the linear band ceramic in Central Europe, and then dispersed into other areas of Northern Africa. But it implies that the Neolithic was a serious nutritional stress on populations, that it actually led to a selective sweep in lactase persistence. And so I'd like to look then at evidence for body size and activity through time in that area of Central Europe as well, including the linear band ceramic. All the work that I'm going to talk about now is work that was done by all the work in Central Europe is work done by a PhD student, a former PhD student of mine, Alison McIntosh, working with Ron Pinhasi. And she looked at these trends through Central Europe in the range of sites you can see here. And I want to show that from the looking at estimated stature and estimated body mass from the Mesolithic hunter-gatherers to the Neolithic, you see a dramatic drop in body mass, followed by a general increase again. That's the increase in stature occurs in both men and women. The drop and increase, it's pretty much the same shape curve. If you look at body mass, though, you can see that the men follow essentially the same curve. Women drops. Well, there's basically no change through time in women from the Mesolithic to the medieval period, and that also suggests both changes in body size through time, but a different change in linear growth versus body mass and perhaps adiposity through time. That's something we need to look at more seriously. But looking at activity levels, these are the torsional strength. Every time you see something that says J there, it means torsional strength. You can see a decline through time from the Neolithic through to the medieval period in largely in males, some fluctuation in females through time. And this is another skeletal indicator which has been sometimes referred to as a mobility index, looking at the shape of the bone. Remember I mentioned shape differences between distance runners and hockey players. Looking at bone shape, you see declines that would be associated with decreasing mobility through time as well. So again, you see that pattern that you saw in Egypt of a decrease and then an increase in body mass accompanied by a steady decrease in activity, which is really, I think, really interesting. You also see changes in other aspects of morphology, and I just wanted to point this out to show that there are multiple lines of evidence pointing to the same thing. Through from the Neolithic through to the medieval period, you see long bones getting straighter, which is something that's been argued to be related to decreasing mobility as well, because the high mobility engenders bending through, influencing the fracture risk of bones. So it's a bit complicated. So very broadly speaking, you can see those same trends of decreasing, increasing body mass, decreasing mobility. And so I wanted to look finally at cultural change through time in China. And this is looking at a range of populations in northern China, and this is work done by a former PhD student of mine, Yun Xiu. And what you notice here, this is dividing. I showed here a range of different archaeological sites that she used, looking at them by subsistence strategy. So we don't have hunter-gatherers in this particular study, but we have pastoralists people who have a mixture of agriculture and pastoralism, agriculturalists and later industrial populations, you can see that stature is basically the same through time. There's no change across 8,000 years in Chinese prehistory, but in terms of femoral head diameter and body mass, you can see basically no change through about 7,000 of those years of Holocene prehistory, and then a dramatic decrease in the industrial period, which I have yet to explain. But if you look at J values, the torsional strength of the femur as a proxy for mobility, you can see a general trend across both sexes of decreasing mobility through time, but the males and females show different relationships. So males are relatively consistent through most of the Holocene and then drop considerably in the industrial period, whereas the women mobility index tends to drop from pastoralism to agropastoralism and then stays relatively consistent. So the timing of that decrease seems to be a little bit variable. To summarize all of that, I think one of the things we can see is people haven't really been looking at phenotypic change through the Holocene and how it may relate to cultural change, but we can see significant phenotypic change in all populations. It's not necessarily consistent, but there are some trends that we can point out that relate each of these different trajectories. One of them is that there's general body mass reduction. That occurs everywhere, but it occurs in different timing. We don't have evidence for that in China, but I suspect we would, I should say, if we had earlier Paleolithic data. In the Near East, that trend starts from the Paleolithic through to the Epipaleolithic. So by 20,000 years ago, people are already smaller in body size and more sedentary. In Central Europe, that occurs later, and it starts with the Mesolithic, but continues afterwards for some period of time. In terms of what we know about biomechanics and activity levels, it occurs, the changes that occur are fairly universal. There's always a reduction throughout the Holocene, but it differs locally. It's not consistently associated with the origins of agriculture, for example. It seems to be variable through time, but the end point always seems to be lower than the starting point. And that's, I think, the main sort of take-home message, is that body size goes down and then rebounds. Activity just keeps going down at some point. It's just the timing's variable. I think all of this suggests a variable risk of changing energy balance through prehistory. And obviously this would relate to disease risk and, under different local conditions throughout the Holocene. So in that context, I think I will leave it there. I wanted to broadly talk about the potential to start to untangle long-term variation in human biology, talk about some of the mechanisms methods we can use to do that. Obviously there are limitations to it, and start to think more about, of course this needs to feed back more with what we know about archaeology and cultural change locally. This is just a very broad picture of human phenotype. So I think I'll leave it there. If there are any questions, I'll be very happy to take them. Thank you.
So there's a lot of heritability and genetic heritability in these characters, but there's also a lot of phenotypic flexibility.
Absolutely.
Have any guess about the relative role of those two forms of adaptation in creating the phenotypic differences?
I mean, based on this sort of data, I don't think we can say. I suspect that phenotypic plasticity is something that can match an organism to its environment, and it can artificially inflate our heritability estimates. In most of these areas, there is, in all of these areas except the Nile, there's good evidence for genetic continuity across these timescales. So I suspect a lot of it is phenotypic plasticity, but I think that's just theoretically I fall more on the plasticity side. generally. So there's not without any good evidence.
Thank you. Very fascinating, broad swath across human history. So I envy that data. But just kind of curious about if fertility and mortality profiles are changing across time.
Yeah.
I know you're limited by the data that
Yeah.
exists in the ground, but how much, if you're not really controlling for the age of distribution of what you're finding, how much of the patterns are really just differential fertility mortality patterns being reflected? Thank you.
There's clearly there haven't been good demographic studies in all of these areas, but there have been for much of Europe and the Near Eastern record, and they do show a very clear. Those studies have focused around the transition to agriculture, and they show, of course, what you would expect of a massive demographic shift. There is a large increase in the number of subadult burials. So there's that. The problem with paleodemography is the subadult burials can indicate either fertility or mortality. If there are more subadults, it means that they're probably more being born, but they're probably more dying, and we can't tell the difference between the two of them. There's definitely a demographic shift. I think the one thing which the way that demography doesn't change, I don't think has much of an impact on what we're seeing, is that I'm really looking at the skeletal indicators are snapshots of terminal growth in adults. So they're looking at an adult at the end of the growth period around the age of, bone biomechanics will reflect probably the loading in the last 7 years of their life, which probably ended around 50 or 60. The body mass and stature indicators really indicate an 18 to 20 terminal growth as a snapshot, and that's kind of independent of the large fluctuations in fertility. I think it's just indicating something about size, energetics, and growth. But
I think maybe there, and then the money.
Thanks very much for a great talk, Jay. Really interesting data that you were showing between hockey players and runners, for example, and that's showing very clearly that depending on what you're doing in life, that you see these patterns. And in this case, you know the patterns. But what I'm curious about, what is the resolution for some of these ancient populations? Is there a possibility of identifying groups that were perhaps doing different kinds of labor, whether it's agricultural or engineering projects? Do you have that resolution? Does the data show that?
I suspect that's a really big problem. I've been working in this area for a long time, and the activity and mobility is the one thing we're most confident in. But I think what I didn't show is I think really interesting is the Bronze Age in a lot of places, particularly in the Near East, is when you get massive task specialization and craft specialization. And there you can't, the one thing that you see is a massive increase in variance in biomechanical profiles. So I showed that a little bit in the Middle Eastern data, where I said that men and women kind of fanned out, and the women were lower, men were higher. But you see that in upper body biomechanics as well. And I think there's a danger if one goes too far, then it's really storytelling of making up shit, which I don't want to do. But and what I'm probably doing anyways. But then I think that diversification is the big story, is how much variance is there, because the hunter-gatherers tend to be tightly, they have a tight range of biomechanical profiles, and those are highly variable. And I think if you looked around this room and characterized everybody's bone based on, there are people who played squash for however many years and people who run, and we would have so much variance that I don't know what it would tell us about this population. So.
And my question is related to the last one. So you characterized or compared these sportsmen in the control group.
Yes.
So have you also taken sort of present-day communities like, hunter-gatherers or nomads or whatever, and then put activity meters on the individuals to do some reality mining on their activity patterns, and then try and look what statistical confidence you have in terms of classifying these types?
I have a rejected NSF grant to do that, which we have a PQCT scanner, which is like about half the size of a car, and submitted a proposal to the NSF to have one custom built so that it would be portable enough to take by helicopter into the highlands of Papua New Guinea. We didn't get it funded, and I don't know how. I think one of the things we're doing is I have some students now who are looking at energetics in the field, because I think that's really what we need to do, but we don't have a way of imaging the internal bone structure yet without bringing this piece of equipment somewhere. So I would absolutely love to do it, and until someone gives us some money, I don't think I'll be able to.
It's fascinating stuff. I wondered, though, why you didn't, or maybe I missed it, but you didn't really talk about inequality. And I was thinking particularly about the first Egyptian graph with the tooth problems and
Yes.
health declining as a result of the beginning of agriculture.
Yeah.
And then it goes right up again in the dynastic period. And that's a period of such incredible inequality.
Yes.
You'd expect if you're sampling randomly, and I know asking you about your data is kind of
Well,
unfair,
I think that study was a first attempt, and I suspect there are some sampling issues that mask the diversity as well. I do think one thing I've learned in my career is when you start out with a dichotomy or a small number of groups and you sample them, you will find some differences that are interesting. As soon as you go and try and replicate it somewhere, it gets really, really complicated. And I suspect that there's a lot more variability in later Egypt. And the Kerma sample, which is 12th dynasty, is a little bit, it's on the edge of the Egyptian empire, and I suspect they had their own independent things going on. So it suggests that there's this amelioration, but if you were closer into the core of the Egyptian empire, you might see a lot more variability based on cemetery, I think.
Hey, so it looked like you were looking at two traits as they changed over time,
Yeah.
like weight and height.
Yeah.
And so it made sense to me that those would both go down and then
Yeah.
come back up, at least weight.
Yeah.
But why would height go down and come back up again?
Well, height is a fairly sensitive reflector of socioeconomic status, health. It's the secular trends that we see almost universally in the world over the last 100 years are a good reflection of that. So in many ways, health as a terminal point of growth should track fairly closely the kind of general environmental conditions during development, I guess, and resource
I
availability.
think it's nutritional stuff.
Yeah.
Is there anything more? Anything at all?
I was interested in because a lot of this is about the joint dimensions, and you're talking about that the cessation at
Yeah.
puberty, and you've got this great kind of sexual dimorphism
Yeah.
that you're showing. Is there any hint at timing? What's happening with timing of puberty?
The timing
from
of
this?
I don't think it's something that I can't think of a good way to. That's one of those biological problems we would love to study. I can't think of a good way to do it. Most life history studies are attempting to look at developmental timing through the teeth and formation of dental enamel and that sort of thing. But it's in terms of timing of fusion of long bones, it's difficult. I don't know of any way to do it really.
Could I ask you to speculate whether it would look a bit like the stature, or what do you think?
That to me is like that's kind of a dream world. I can't imagine. I just don't know. Yeah, I really don't know. I'm sure there would be there's so much variability in timing of menarche in modern humans and it correlates with energy. I'm sure you would see similar patterns. Yeah.
Anyone else? Okay, if that's all, let's join me in thanking Jay.
I did forget to thank my collaborators and students and everything. So I do note that there are a lot of people involved. Thank you.